112 degrees. In May. That number should not exist right now, and yet the National Weather Service just put it in writing. An official forecast, not a worst-case scenario, not a model outlier. A forecast. 3 extreme heat warnings active simultaneously across the Southwest. A Denver record from 1915 standing on its last legs, and a pattern that is now repeated 3 consecutive months in a row without the El Niño that should be driving it. Someone forgot to tell the atmosphere what month it is. Or maybe the atmosphere knows exactly what month it is, and simply stopped caring. Stay with me until the end, because what I'm about to show you is not a weather story. It is something much harder to explain. Before we get into it, if you are new here, hit like and subscribe to The Quiet Archivist, because we are following every thread of this story. The ENSO data that should be explaining this, but cannot. The land-atmosphere feedback loop that has been loading since March like a slow-motion trap. And the deeply uncomfortable possibility that the heat pattern Americans think they understand is operating on a timeline that our seasonal forecasting frameworks are not built to anticipate. There are threads here that are still unraveling, and you do not want to miss where they lead. Now settle in, and let's get into it. Something is wrong with the calendar. Right now, as you watch this, 3 extreme heat warnings are active simultaneously across the American Southwest. Not 1, not 2, 3. And one of them, covering Imperial Valley, the Salton Sea, the entire Coachella region, is forecasting 112 degrees Fahrenheit. In early May, at a time of year when most of the country is still arguing with itself about whether it needs a jacket in the morning. Let that number sit for a moment. 112 degrees Fahrenheit. That is not a misprint. That is not a record from some distant, hotter era being recited for dramatic effect. That is the forecast. That is what the National Weather Service is telling the people who live in that region right now. Stay inside. Do not go outside. This is dangerous. And just so we are absolutely clear on what an extreme heat warning actually means, this is not a yellow advisory. This is not a polite caution. This is the highest tier of heat alert the National Weather Service issues. It is reserved for conditions that are not just uncomfortable, but genuinely life-threatening. The kind of heat that kills people who are unprepared, who are elderly, who are working outside, who do not have air conditioning, who make the mistake of thinking they can handle it because they have handled hot days before. To see 3 of them active simultaneously across that much geography in the first 2 weeks of May is, and I want to use this word carefully, rare. Not unusual for the region rare. Not we haven't seen this in a few years rare. Rare in the way that makes professional meteorologists stop what they are doing and stare at the screen. Phoenix is sitting at a forecast of 105 to 109 degrees Fahrenheit. The National Weather Service has classified the Phoenix Metro under their major heat risk category, the kind of classification that in June or July registers as uncomfortable but expected. In May, it registers as something that requires a different kind of explanation. And then there is Denver, forecast to reach 89 to 91 degrees Fahrenheit by May 13th, which, if it happens, would tie or break a temperature record that has stood since 1915, 111 years. Through the Dust Bowl of the 1930s, through every El Niño event in the modern record, through every drought decade, every anomalous summer, every fraction of every degree of post-industrial warming that has been added to the global baseline since the early 20th century. That record has survived all of it. Until now, possibly. Here's the detail that makes this especially strange, the one that professional meteorologists keep coming back to. The current ENSO index, that is the measure of El Niño and La Niña activity in the tropical Pacific Ocean, the great oceanic engine that typically shoves and steers American weather into its most extreme configurations, is sitting at approximately plus 0.1. For reference, a strong El Niño reads at plus 1.5 or higher. A strong La Nina reads at minus 1.5 or lower. Plus 0.1 is essentially flat, essentially neutral. No strong El Niño, no strong La Nina, no significant tropical Pacific forcing of any meaningful kind. Whatever is happening over the American Southwest right now, the usual suspect is not in the room. The alibi checks out, which means something else is doing this, and we have to figure out what. So let us frame this correctly, because the framing matters more than the individual temperature readings. The atmosphere is behaving like July. The calendar says May. This is not extreme summer heat arriving a little early. This is summer heat showing up 6 weeks before its scheduled arrival, uninvited, and acting like it owns the place. The question on the surface is whether this is unusual. It obviously is. But the deeper question, the one that should be pulling at you, the one I am going to spend this entire video building toward, is whether this event is isolated. Whether it is a random spike in an otherwise normal year. Whether it is the kind of anomaly that makes headlines today and gets forgotten by next month. I already know the answer to that question. And when I tell you, you are going to want to keep watching. Let us talk about what May 11th is supposed to look like in Phoenix, Arizona, because understanding the violation requires first understanding the baseline it is violating. On any given May 11th, built from over a century of recorded temperature data, Phoenix averages a high temperature of around 90 degrees Fahrenheit. That is its climatological normal for that specific date. 90 degrees is already warm. It is a desert city. Warm is the default setting. But 90 degrees is the unremarkable, nothing unusual here, same as it always is value for that exact calendar position. The current forecast is 109 degrees. That is a departure of roughly 19 degrees Fahrenheit above the climatological average for that specific calendar date. Not above average for the year. Not above average for the season. Above average for that exact moment on the calendar. The date the Earth occupies on its orbit, the sun angle it produces, the day length it delivers. To put that departure into human terms that require no meteorology degree, imagine your doctor tells you your normal resting body temperature is 98 degrees Fahrenheit. And today, you walk in with a reading of 117. You would not be having a polite, measured conversation about whether that was slightly elevated. You would already be in an emergency room. What makes it genuinely strange, beyond just the raw number, is where Phoenix actually sits in its seasonal arc. Phoenix's peak heat, the hottest stretch of the year, the period when temperatures regularly push into the 110 to 115 range, normally occurs in late June through July. The city has a seasonal progression. It builds gradually through May and into June, peaks in late June and early July, and then slowly descends through August and into fall. What we are watching right now is not the leading edge of that arc running slightly ahead of schedule. The full, mature, midsummer high-pressure configuration has simply arrived 4 to 6 weeks before its time. The seasonal system has been skipped. What is driving that skip is something called a 500 millibar height anomaly. And I know that sounds like jargon designed to make your eyes glaze over. So let me translate it. The atmosphere has layers, and those layers have measurable thickness. When air in a column is warm, it expands, and the column gets taller. Meteorologists measure the height of the 500 millibar pressure level, roughly the midpoint of the atmosphere in terms of pressure, as a way of reading the thermal character of the air mass below it. A reading of 588 decameters at that level over the American Southwest is what the atmosphere looks like at the peak of summer. It is the signature of a hot, baking, compressed air column, sitting over the region like the sealed lid of a slow cooker, cranked to maximum. Right now, in early May, that value over the southwest is 588 decameters. August values, May dates, one atmospheric fingerprint transplanted into the wrong position on the calendar. Cast your eye to the north and east, and the contrast becomes almost theatrical. While the Sonoran Desert is reading August, the Rocky Mountain snowpack is still melting. Spring storm systems are still spinning across the northern plains. The country is not in summer. Most of it is in the messiest, most transitional part of spring. Two atmospheric seasons running simultaneously on the same continent, divided by the edge of one high-pressure system. And where two seasons collide at a sharp boundary, something tends to happen. Something that does not stay contained to one region, does not stay polite, does not wait for the rest of the calendar to catch up, which is exactly the next part of the story. On the same day that Imperial Valley is forecast to reach 112 degrees Fahrenheit, North Dakota is under frost advisories. Same country, same moment. One region bracing for temperatures that would be dangerous in the middle of July. Another region warning farmers and gardeners that overnight temperatures may approach freezing. And understanding why those two facts are not coincidental, why they are causally connected expressions of the same atmospheric structure, requires understanding something about how the atmosphere stores and releases energy. Temperature gradients across the surface of the Earth are the atmosphere's primary energy reservoir. The bigger the temperature difference between two adjacent regions, the more energy is available for the atmosphere to convert into motion, pressure differences, wind, and storm development. An 80-degree temperature spread between the desert southwest and the northern plains on the same day is not just a dramatic contrast. It is a loaded spring, and loaded springs release. That is what they are for. The eastern and northeastern edge of a heat dome, the boundary zone where the baking, high-pressure air mass of the southwest meets the cooler, more dynamic air to the north and east, is one of the most storm-productive zones on the planet when conditions align correctly. Warm, moist air from the Gulf of Mexico flows northward along the eastern flank of the high-pressure system, drawn upward by the pressure gradient at the dome's margin, and collides with the drier, cooler air behind any frontal boundary in the region. The result is the kind of atmospheric instability that produces organized, severe thunderstorm development. Not ordinary afternoon pop-up storms. The rotating updraft kind. The kind that generates large hail, destructive straight-line winds, and under the right conditions, tornadoes. The Storm Prediction Center's outlooks for Oklahoma and Texas during this period reflect those ingredients with unusual clarity. The setup is not subtle. It is textbook severe weather, delivered by the heat dome's pressure gradient acting as the organizing mechanism. On the western and southern margins of that same heat dome, a different category of hazard is being assembled with equal efficiency. Low relative humidity, values dropping to 10 to 20% in the afternoon hours. Sustained winds at 20 to 35 miles per hour, with higher gusts over exposed terrain. Vegetation that is not fully greened up, or that greened up early under the anomalous warmth of March and April, and is now stressed and partially dried out. Accumulated dead fuel on the surface. Red flag conditions, active across the southern and high plains. One ignition source, a downed power line, a discarded cigarette, a lightning bolt from one of the severe storm systems developing to the east, and you have a fire environment capable of extreme, rapid, difficult to suppress behavior. So step back and take the full frame at once. 112 degrees in the California desert. Frost advisories in North Dakota. Severe storm risk across Oklahoma and Texas. Red flag fire weather across the high plains. All of it simultaneously. All of it driven by the same distorted, early season atmospheric configuration. This is not several unrelated weather stories running in parallel. This is one story told simultaneously in 4 different languages across 4 different regions of the same continent. The system is not balanced. It is stretched across its own extremes. And stretched systems, in atmospheric dynamics as in everything else, are systems looking for a release point. Which brings me to one specific city, at one specific elevation, where the release of all of this energy is about to be measured against a number that has not moved since the early 20th century. On some otherwise unremarkable day in May of 1915, Denver, Colorado recorded a high temperature of 90 degrees Fahrenheit. A century and more of weather happened after that. The record stood. That longevity is itself a piece of scientific data, and it deserves genuine appreciation. Denver sits at the edge of the Rocky Mountains, at the boundary where warm air from the south and cold air from the north routinely collide, where Chinook winds can push temperatures 30 or 40 degrees in a single afternoon, where the weather is structurally volatile and historically difficult to predict. It is not a city known for stable, boring, hard-to-surprise meteorology. And yet, for 111 years, no early May atmospheric configuration managed to push Denver past 90 degrees on that section of the calendar. Through every drought, every anomalous spring, every year that climate scientists would describe as an outlier, the record held. Think carefully about what that implies. The average global temperature in 1915 was roughly 1 degree Celsius cooler than today's baseline. That might sound modest, but in the context of atmospheric extremes, 1 degree Celsius of baseline warming translates into meaningfully altered probability distributions for rare events. The tails of the distribution get fatter. Events that were previously rare become less rare. Events that were nearly impossible become merely uncommon. 1 full degree of global average warming should statistically have made the configuration required to break Denver's May record somewhat more probable in every subsequent year. And yet, here we are, 1 degree warmer than the world that produced that record, and it has taken until 2026 for May in Denver to credibly threaten to erase it. That gap between what the baseline warming suggests should have happened by now and what the observational record actually shows tells us something important about the difference between gradual background warming and specific atmospheric configuration. Breaking Denver's 90-degree May record does not just require warmer air. It requires the heat dome to be positioned at precisely the right latitude and longitude, tilted at the correct angle, deep enough and persistent enough to push warm air up against the front range of the Rockies and force it down into the Denver Basin. Warmer baseline temperatures make that configuration slightly more probable in a statistical sense. But the configuration still has to actually materialize. In most years, it does not. In 2026, it apparently does. And that is what makes this moment a diagnostic test rather than just a weather curiosity. Records are not simply temperature numbers. They are encoded atmospheric history. They tell you that on this date, in this location, the most extreme configuration the system ever produced generated exactly this result. When you tie that record, you confirm you have reached the historical ceiling. When you break it, you confirm the ceiling has moved. When you break it by multiple degrees, by 2 or 3, as some ensemble model members suggest is within the range of possibility, you are no longer incrementally extending the record. You are demonstrating that the atmospheric system can now produce, at this specific point on the calendar, configurations that the entire previous history of observations did not contain. You are in unmapped territory. Denver is not the central character of this story. Denver is the instrument. It is positioned precisely on the edge of the historical record, calibrated by 111 years of continuous observations, ready to tell us in measurable and undeniable degrees exactly how far outside the envelope this moment is operating. And the reading it produces will matter, not just as a meteorological fact, but as a data point in a sequence that, once you see it clearly, is one of the most significant atmospheric stories of the decade so far, because this heat dome is not the first event of 2026. It is the third consecutive one. And the first two were not mild. They were not warm spells. They were historically significant record breakers that somehow did not generate the sustained alarm they deserved. Which means the real story is not this week's forecast. The real story is the pattern behind it. Here is something that deserved far more attention than it received. In March of 2026, 2 months before the event you are watching now, 14 states across the United States broke all-time March temperature records. Not daily records for individual weather stations. Not records for a specific week within the month. All-time state records for the entire calendar month of March, representing the highest temperatures ever observed in those states in that month across the entire modern period of instrumental observation. 14 of them, simultaneously or within days of each other, driven by a single coherent atmospheric event. Approximately 150 daily temperature records fell during the same period, along with roughly 50 monthly records at individual stations. Phoenix, Arizona reached 112 degrees Fahrenheit in March. To understand what that number means, you need a reference point. Phoenix's average high temperature in mid to late March is somewhere around 75 to 80 degrees Fahrenheit. 112 degrees in that window is a departure of 30 or more degrees above the climatological average for that calendar position. That is not a warm spring day. That is not an unusually early taste of summer. That is a full, mature, midsummer atmospheric configuration dropped onto the calendar 3 full months before its natural season. It is the atmospheric equivalent of opening your front door in what you believe is October and finding July standing on your porch. Then April arrived. April was quieter. Not cold, not a reset, not a return to anything resembling seasonal normal, but quieter in the sense that the dramatic record-breaking pace of March slowed. The ridge patterns over the west weakened at the surface level, but did not collapse at the levels in the atmosphere that matter most for sustained anomalies. Temperatures across the western United States remained consistently above seasonal norms throughout April, without triggering the kind of emergency level alarm that March had generated. To the casual observer, to the news cycle that rewards novelty and forgets continuity, April looked like the system coming back to its senses. Like the come down after a spike. It was not a reset. It was a holding pattern. And now, in May, the third heat dome of the year is building, and it is not weaker than its predecessors. In some metrics, according to ensemble model guidance, it may be stronger. This is the concept meteorologists and climate scientists are increasingly calling heat stacking, and it is one of the most important and systematically underreported dynamics in current extreme weather science. Each heat dome in a sequence does something to the land surface that makes the next event easier to produce and harder to break. It dries the soil. Dry soil cannot moderate surface temperatures through evaporation because it has no moisture to evaporate. Every photon of solar energy arriving at a dry surface goes directly into heating that surface, rather than being consumed by the phase change from liquid water to water vapor. The surface gets hotter. The hot surface heats the air above it. The hotter air amplifies and sustains the high-pressure system. The high-pressure system continues to suppress the rainfall that would replenish soil moisture. The loop runs forward. The land becomes an active participant in its own warming rather than a passive recipient of atmospheric conditions. The media has been covering these 3 events as separate stories. Heatwave in March, warm spring in April, new heat dome in May. 3 individual news cycles, each generating its brief moment of alarm and its brief moment of forgetting. What the coverage has consistently failed to do is connect them as a sequence, as a system that is not returning to its pre-event baseline between iterations, but is instead compounding, feeding forward, inheriting from each predecessor a land surface that is slightly drier, slightly more thermally loaded, slightly more predisposed to amplify the next event. The repetition is not the background. The repetition is the signal. And reading that signal clearly requires confronting a question that the standard meteorological explanatory framework cannot comfortably answer. El Niño and La Niña are the atmosphere's most reliable scapegoats, and right now they cannot be blamed for anything. ENSO, the El Niño Southern Oscillation, describes the periodic warming and cooling of sea surface temperatures across the central and eastern tropical Pacific Ocean, driven by coupled interactions between the ocean and the overlying atmosphere. When El Niño conditions develop, a large pool of anomalously warm ocean water spreads across the equatorial Pacific, altering the temperature gradients that drive planetary-scale atmospheric circulation. Jet streams shift, storm tracks reorganize, precipitation and temperature patterns across North America change in ways that have been documented and quantified across decades of observations. A strong El Niño is one of the most powerful near-term climate forcing mechanisms on the planet, capable of producing significant temperature and precipitation anomalies across entire continents. La Niña does the opposite: cold water to the surface, reversed atmospheric reorganization, different regional consequences. Strong La Niña events are associated with increased drought risk across the American Southwest, elevated fire danger, and stronger than average hurricane seasons in the Atlantic. Between those two active states is exactly where we currently are. ENSO neutral. The tropical Pacific is not doing anything significant. The index reads plus 0.1. By the standard explanatory framework for American weather extremes, neutral ENSO should not be producing a triple heat dome sequence that is threatening century-old temperature records in May, while simultaneously generating fire weather, severe storms, and anomalous heat across the entire continental United States. The textbook says this should not be happening at this scale without a tropical Pacific driver. And yet here we are. This creates what atmospheric scientists describe as a forcing attribution problem. When you observe a persistent continent-scale anomaly and your primary explanatory variable is absent, you face a choice. Either the event was produced by pure internal atmospheric variability, the random, chaotic fluctuations that a complex system can generate without any external forcing, or you need to look for a different driver that was not adequately weighted in your initial analysis. Internal variability is genuinely real. The atmosphere is a chaotic system and can, through the random evolution of its own internal wave patterns and circulation features, produce extreme configurations without any external cause. The question is whether what we are observing in 2026 sits within the statistical envelope of what known internal variability can plausibly explain, or whether it exceeds that envelope in ways that require additional explanation. 3 structurally similar heat dome events in 3 consecutive months, each generating significant records, each occurring without strong external tropical forcing, each leaving the land surface in a more preconditioned state for the next event. This combination sits in a region of probability space that warrants serious scientific attention. It does not prove that something beyond internal variability is operating, but it raises the question with enough force that dismissing it as simple bad luck requires more statistical justification than is currently available. 3 interpretations deserve honest evaluation. The first is random clustering. Rare events occasionally pile up by pure chance, and this may be one of those times. Uncomfortable, memorable, but ultimately a statistical fluctuation that will not persist. The second is pattern-locked circulation. The large-scale atmospheric flow has settled into a preferred mode, a quasi-stationary wave configuration that keeps rebuilding similar ridging structures over the American West, regardless of what is happening in the tropics. This explanation is the most consistent, with what the observations actually show. A structurally similar high-pressure ridge reappearing in March, April, and May, not in identical form, but with recognizable geometric similarity in its position and shape across all three events. The third interpretation is the most consequential and the least certain, that the background state of the climate system has shifted sufficiently to make these persistent, anomalous early season ridging patterns structurally more probable than historical statistics would suggest. That we are not just watching a cluster or a temporary pattern lock, but a fundamental redistribution of where the atmospheric circulation prefers to spend its time. All three explanations almost certainly contain partial truth. The question of their relative contributions is not yet precisely resolved. What is clear is that the mechanism most consistent with pattern-locked and potentially regime-shifted circulation points not to the tropics, but to the polar regions, to a chain of physical processes that begins at the Arctic Circle and ends at the jet stream over the American Southwest. A heat dome sounds like it should be a complicated thing. The basic physics are almost elegantly simple. High-pressure systems are regions where air is descending rather than rising. In a low-pressure storm system, air converges at the surface, rises through the atmospheric column, cools as it ascends, and produces clouds and precipitation. In a high-pressure system, the process is reversed. Air aloft diverges and spreads outward, and the net result is a persistent, organized downward motion through the atmospheric column. Descending air has a specific and important thermodynamic property. It warms as it descends. The mechanism is called adiabatic compression. As air moves downward into regions of higher atmospheric pressure, it is compressed. Compression converts potential energy into thermal energy. The air gets warmer, not because it absorbed heat from somewhere else, but because the act of compression itself generates heat. By the time that descending air reaches the surface, it has been actively heated by its own downward journey. Now, layer the feedback loops on top of that basic mechanism. High pressure suppresses cloud formation because clouds require rising, cooling air to develop. The exact opposite of what is happening in a high pressure system. No clouds means unimpeded solar radiation arriving at the surface. More solar radiation heats the surface more intensely. A hotter surface heats the overlying air more aggressively. Warmer air is less dense, and a column of less dense air produces higher pressure at the levels aloft where meteorologists measure atmospheric dynamics. Higher pressure aloft means stronger and more persistent sinking motion. Stronger sinking means more compression heating, less cloud cover, more surface radiation. The loop reinforces itself at every step, always in the same direction. The heat dome does not gently fade on its own. It persists and often intensifies until a sufficiently large external atmospheric disturbance arrives to displace it. The jet stream is the only force reliable enough to do that displacing. The jet stream, the fast-moving band of air circling the northern hemisphere in the upper troposphere, is what determines how quickly or slowly weather systems move across the continent. When the jet is strong and fast, weather systems transit the country efficiently. Cold fronts arrive, break ridges, allow heat domes to move on. When the jet is weak or meandering, weather systems stall. Heat domes persist for days or weeks instead of moving through in 2 or 3 days. The difference between a dangerous but manageable 3-day heat wave and a genuinely catastrophic 10-day event often comes down to whether the jet stream is behaving normally or has gone into what meteorologists call a blocking pattern, a configuration where the normal westerly flow breaks down and the atmospheric circulation stalls. The jet stream is driven and maintained by the temperature gradient between the warm tropics and the cold polar regions. Strong gradient, strong jet. Weak gradient, weak and meandering jet. And here is where the Arctic enters the story in a way that is both physically coherent and deeply concerning. The Arctic has been warming roughly 2 to 4 times faster than the global average over the industrial era, a well-documented phenomenon called Arctic amplification. As the polar regions warm disproportionately fast, the temperature contrast between the equator and the poles narrows. The gradient that drives the jet stream weakens. A weakened jet is more prone to the high amplitude, slow-moving, blocking wave patterns that allow heat domes to anchor themselves over a region for extended periods, rather than moving through on a normal timescale. This hypothesis, Arctic amplification weakening the jet stream and increasing the frequency and persistence of atmospheric blocking, is one of the most actively debated topics in current climate science. There are credible researchers who find supporting evidence in the observational record and in model experiments. There are equally credible researchers who argue the signal is too noisy, the record too short, and the causal chain too complex to establish definitively. The science is not settled in the way that the basic physics of greenhouse warming are settled. It is a live scientific question with genuine expert disagreement. What is not a live question is the phenomenology itself. The blocking events are happening. The quasi-stationary ridges are appearing with the kind of persistence that produces the most extreme outcomes. The heat domes are lasting longer and arriving earlier than historical baselines would predict. Whatever the underlying mechanism, and the Arctic amplification pathway remains the most physically coherent candidate. The behavioral signature of a weakened, more easily blocked jet stream is present in the observational record. In 2026, it has expressed itself 3 times in a row, across 3 consecutive calendar months, compounding with each iteration, which leads directly to the question of what that compounding looks like on the ground. Not in the atmospheric column, not in the jet stream dynamics, but in the land and the air, and the fuel that is sitting underneath all of this and waiting. Red flag warnings are not issued casually, and right now they are active across the southern and high plains. A red flag warning requires the simultaneous presence of a very specific combination of conditions. Relative humidity typically below 15 to 20%. Sustained winds above 20 miles per hour, with higher gusts, and dry fuel moisture content in the vegetation and accumulated material on the surface. These 3 factors together create a fire environment where any ignition from a downed power line, a discarded cigarette, a lightning strike from a passing storm, has the potential to produce extreme, rapid fire behavior, rapid spread rates, high flame lengths, long-range spotting from embers carried downwind, the kind of fire growth that outpaces suppression resources and creates genuine life safety emergencies for anyone in the path. What makes the fire situation particularly serious right now is not just the current meteorological conditions. It is the preconditioning history. March dried the soils and stressed the vegetation across a broad swath of the west and plains. April failed to replenish what March removed. The southwest and southern plains entered May with soil moisture deficits that would climatologically not normally appear until the peak of late summer. The fuel moisture values in the grasses and shrubs across the fire risk zones reflect months of accumulated drying, not just the conditions of the past few days. The heat dome did not create this risk from scratch. It inherited a landscape that the entire preceding spring had been systematically preparing for ignition. At the eastern margin of that same heat dome, a completely different but equally serious atmospheric hazard is operating. The pressure gradient between the superheated interior of the high-pressure system and the cooler, moister air to the north and east is drawing Gulf of Mexico moisture northward into the southern and central plains. That warm, humid, unstable air is encountering the drier, cooler air behind the frontal boundaries at the edge of the dome's influence, and the collision is producing organized, severe thunderstorm development across Oklahoma, Kansas, and Texas. These are not ordinary afternoon convective storms. They are forming in an environment with significant vertical wind shear. The change in wind speed and direction with altitude that allows thunderstorm updrafts to rotate. Rotating updrafts are the precursor to supercell thunderstorms. Supercells produce large hail, destructive winds, and tornadoes. The Storm Prediction Center's outlooks for this region are not borderline. The ingredients are clearly present and well organized. The point I want to drive home here, because it gets lost in weather coverage almost every time, is that the extreme heat in the desert and the severe storms in Oklahoma are not two separate weather events happening to coincide. They are causally connected. The heat dome creates the pressure gradient that draws the Gulf moisture northward. The Gulf moisture fuels the storm development. The storms occur at the exact location where the heat dome's margin meets the cooler air mass, which is where the instability is maximized. Remove the heat dome, and you remove the organizing structure that gives this severe weather outbreak its intensity and positioning. They are the same story told in two different meteorological dialects. Now pull back further and take the national view, because when you do, something becomes visible that the regional analysis cannot convey. Florida is recording heat index values, the feels-like temperature accounting for humidity, in excess of 100 degrees Fahrenheit in early May, before summer has genuinely arrived. The western deserts are under extreme heat warnings. The northern plains are simultaneously experiencing fire weather and frost advisories. The southern plains are under severe storm risk. Every major geographic region of the continental United States is currently at the edge of a significant atmospheric hazard, and every one of those hazards is a regional expression of the same underlying blocking ridge and the pressure gradient structures it creates. This is continental synchronization of atmospheric extremes, and it is not normal. Under ordinary atmospheric conditions, the country is regionally asynchronous. Weather variance distributes extremes unevenly. Some regions are warm when others are cool. Some are stormy when others are calm. The randomness of atmospheric behavior, even in a warming climate, typically ensures some degree of geographic diversity in conditions across the continent at any given moment. What we are watching right now is an unusual compression of that diversity. A single dominant atmospheric configuration is asserting influence over the entire map simultaneously, pushing every region toward its hazard threshold at once. And the question of what has made this configuration so dominant, so persistent, and so geographically far-reaching remains the central unanswered question of this entire story. A question that the Denver thermometer is about to provide one more data point toward answering. Every time something genuinely unusual happens in the atmosphere, two alternative explanations reliably appear. And since this channel takes alternative explanations seriously rather than reflexively dismissing them, I want to address both directly and honestly. The first involves atmospheric manipulation, and specifically the High Frequency Active Auroral Research Program, HAARP. Let me be straightforward. HAARP is real. It has operated under enough historical opacity to reasonably fuel public curiosity, and the questions people ask about it are not stupid questions. The conclusion that it is responsible for continental-scale heat domes is not supported by the energy accounting, and the reason is not classified. It is arithmetic. A heat dome covering 3 to 4 million square kilometers at temperatures 10 to 20 degrees Fahrenheit. Above normal contains excess thermal energy on the order of 10 to the power of 20 to 21 joules, stored in the atmospheric column above that domain. HAARP at its maximum operational power output delivers approximately 3.6 megawatts of radio frequency energy, which over a full day of continuous operation works out to roughly 3 times 10 to the power of 11 joules delivered to the ionosphere. Compare those two numbers. The heat dome contains approximately 10 to the power of 20 joules. HAARP delivers 10 to the power of 11 joules per day. That is a difference of 9 orders of magnitude, 1 billion times smaller. This is not a marginal energy mismatch that could be bridged by invoking efficiency or cascading effects. It is a gap so large that no physically coherent causal pathway can close it. A birthday candle cannot melt a glacier. The numbers do not allow it, regardless of how cleverly the candle is aimed. The genuinely uncomfortable truth, and I say uncomfortable because it offers no satisfying external actor to blame, is that the most powerful, best documented, most physically coherent mechanism capable of producing a continental scale heat dome of this magnitude, at this timing, with this degree of historical novelty, is the climate system itself operating exactly as physics predicts it should, under the forcing conditions it has been accumulating for over a century. The unknown in this story is not a hidden actor running a secret program. The unknown is the irreducible complexity of an atmospheric system so vast and nonlinear that even the most sophisticated models in the world cannot fully resolve its behavior. That kind of uncertainty is more honest and, in some ways, more unsettling than any alternative explanation would be. The solar angle is worth taking more seriously, and I mean that genuinely. This is the quiet archivist, after all. Solar cycle 25 has been running more active than initial heliophysics forecasts predicted. Sunspot numbers, solar flare frequency, and the rate of coronal mass ejections have all been tracking above the official forecast curve for this cycle. The solar maximum for cycle 25 falls approximately in the 2025 to 2026 timeframe, meaning we are at or very near the peak of solar activity right now. That is a real and relevant fact. The question is whether that solar activity is sufficient to explain what we are observing. Total solar irradiance, the raw amount of energy the sun delivers per unit area at Earth's orbital distance, varies across the solar cycle by approximately 0.1% from minimum to maximum. The surface temperature response to that irradiance variation, as quantified across multiple research groups and observational datasets, is in the range of 0.05 to 0.1 degrees Celsius over the full cycle. That is a real signal. It is not zero. But it is also not sufficient to explain a heat dome producing temperatures 19 degrees Fahrenheit above May climatology over the American Southwest. The orders of magnitude are wrong in a different direction here than with HARP, not too small in a dramatic way, but simply too modest to be the primary driver of what is being observed. Geomagnetic conditions during this specific event are quiet. No significant solar storms are currently impacting Earth's magnetosphere. The stratospheric chemistry effects of elevated solar ultraviolet near-solar maximum can influence tropospheric circulation through what researchers describe as a top-down dynamical pathway, and there is genuine published science on this mechanism. But its quantified contribution to tropospheric temperature anomalies is considered secondary to surface forcing. The sun is real background signal here. It is not the trigger. The trigger lives in the troposphere, in the blocking ridge, in the jet stream dynamics, in the land-atmosphere feedbacks that have been running in the wrong direction since March. And that system is now approaching its most visible and measurable moment. The moment when every thread of this story converges on a single thermometer in Denver and the 111-year-old number it is about to challenge. Let us close this out, and let me say something that I want to leave with you past the meteorology and past the data. 3 heat domes, 3 consecutive months, a ENSO index that cannot explain any of them, a land surface that has been progressively drying and thermally loading since early spring, a jet stream showing the persistent, quasi-stationary blocking signatures that produce the most extreme outcomes, a continent simultaneously under pressure from extreme heat in the west, fire weather in the plains, severe storms in the south-central states, dangerous heat indices in the southeast, and frost advisories in the north. All of it simultaneously from the same atmospheric configuration. Denver is the instrument through which this moment will be precisely measured. The record is 90 degrees Fahrenheit standing since 1915. The forecast brings the city to the edge of that number, and some model ensemble members suggest it could be exceeded by 2 or 3 degrees. If Denver ties the record, the historical ceiling has been reached. If Denver breaks it, we confirm new territory. If Denver breaks it by 3 degrees, if the thermometer reads 93 in the second week of May, we are not looking at an incremental record extension. We are looking at a demonstration that the atmosphere can produce, at this specific calendar position, configurations that 111 years of continuous observation never contained. That is not a weather story. That is a statement about the operational range of the climate system at a point in its evolution. The central question, the one this entire video has been building toward, is whether we are watching a cluster or a regime shift. A cluster is a statistical anomaly. Rare events sometimes pile up in time through the random behavior of a complex system. 3 remarkable events in a row, generating significant records, occurring in an ENSO-neutral year, uncomfortable, but not impossible under pure internal atmospheric variability. A cluster eventually ends. The system regresses toward the mean. The year is filed as an extraordinary outlier, and the baselines are updated slightly to accommodate it. A regime shift is something qualitatively different. It is when the atmospheric system moves from one preferred mode of operation to another. When the distribution of possible weather states relocates to a new range, and the configurations that used to define normal are no longer the ones the system gravitates toward. Climate history contains regime shifts in both the geological record and the shorter instrumental record. They are almost never recognized in real time. They are typically announced not by a single catastrophic event, but by a succession of events that each appear, individually, to be extraordinary anomalies, and only reveal their true nature when enough of them have accumulated to make the new distribution visible against the noise of natural variability. The honest position, the one I can defend without exaggerating the evidence or minimizing it, is that we do not yet know which of these 2 things we are watching. 3 events is not sufficient sample size to distinguish a cluster from a regime shift with the statistical rigor that attribution science requires. The mechanisms are too complex. The system has too many interacting parts. And the uncertainty is genuine, not rhetorical. What I can tell you is what the structural factors favor. The land-atmosphere feedbacks are running in the amplifying direction. The Arctic amplification signal continues to grow with each passing decade. The background warming trend shows no indication of pausing or reversing. The jet stream dynamics that produce persistent blocking are operating on a planet with a different energy balance than the one that generated the historical baselines we keep comparing our observations against. Every structural indicator points toward more frequent, more intense, and more early season extreme heat events, not toward fewer. The probability distribution is not returning to 1915. The question is how far it has moved and how quickly it continues to move. We do not yet know what 2026 is. We do not know if Denver breaks its record or merely ties it or falls just short. We do not know if the May heat dome is the last significant event of the year, or if summer will arrive carrying the same displaced, anomalous intensity that has characterized every month since March. We do not know if the soil moisture deficits accumulated since early spring will be replenished by a wet and cool summer, or if the same blocking tendency that has dominated the year so far will persist and compound further into the warm season. These are genuinely open questions with genuinely unknown answers. What is not open is what the instruments are recording. What is not open is that the sequence of events in 2026 sits outside anything the modern observational record has shown at these calendar positions. What is not open is that the standard explanatory frameworks, ENSO, solar variability, ordinary internal variability operating against a static climate background, are insufficient individually or in combination to fully account for what is being observed. And what is not open is that the pattern, viewed as a whole rather than as a series of separate events, is carrying a signal that deserves to be read as a signal rather than dismissed as noise. The atmosphere is speaking in a language that is new enough to be genuinely difficult to translate in real time. The individual words it is using, record temperatures, persistent blocking, early season extremes, continental synchronization of simultaneous hazards, are each familiar from the scientific literature. But the sentence it is constructing from those words, in this sequence, at this pace, at these calendar positions, in the absence of the forcing mechanisms that would normally be required to produce it, is one that the scientific community is still in the process of learning how to read. We do not yet know what this is. We know it should not be happening this way. We know the physics that produce each individual component are real and understood. What none of us can tell you, what no one on Earth can tell you with confidence right now, is whether the orchestration of those components into this specific, repeated, compounding, continent-wide pattern represents the atmosphere settling into a new normal, or the atmosphere in the process of deciding whether to. That distinction between a system that has already crossed a threshold and a system that is approaching one may be the most consequential question in Earth science right now, and the answer is being written into the observational record one data point at a time, one broken record at a time, one anomalous month at a time. The record from 1915 has stood for 111 years. Whatever the thermometer in Denver reads on May 13th, write it down. Remember it. Because in 5 years, or 10 years, or 20 years, when someone is trying to understand when the pattern became unmistakable, they are going to look back at 2026 and ask how many people were paying attention. Make sure you were one of them.